The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
On the number 2, 2.3,
Yeah.
it says if the coder, when it tries the value to 0 would be the same. So
Yeah.
I thought it was you were generating random values for that.
You were, but if you look at what totes 0 is collecting, so if you look at the where it draws a random number, J is indexing in totes, right? So when J is 0, your standard deviations, which is also being indexed by J, is going to be 0. Yeah. So you're always going to get the same value.
Okay. Okay.
Any questions? Oh, okay. That was easy. So in lecture, we were talking a lot about or clustering, or we've been talking about clustering in the past, was it 2 lectures? And we had 2 different types of clustering methods. What were they?
Hierarchical and k-means.
Hierarchical and k-means. So can someone give me a rundown of what the steps are in hierarchical clustering? So
when it breaks everything down into one cluster, and then starts merging them together.
So let's say I have a bunch of data points. What would be the first step? So we're going to first assign each point to a cluster, right? So each point gets its own cluster. And then the next step would be what? Right, so you're going to find the 2 clusters that are closest to each other and merge them. So in this very contrived example, it would be these guys. And then you're going to keep doing that until you get to a certain number of clusters, right? So merge these 2, then you might merge these 2, and you might merge these 2, et cetera, right? So you're gonna set the number of clusters that you want at the outset. So for I guess for the mammalian teeth example, there was a stopping criteria of 2 clusters, if I'm not mistaken. Yeah. So if we look, so let's take a look at the code here that implements the hierarchical clustering. So this is just some infrastructure code. It builds up the number of points. We have a cluster set class, which we'll go over in a second. And then we just add, for each point, we're going to create a cluster object and add it to the cluster set. So let's take a look at the cluster set. Cluster set has one attribute, it's the members attribute, and it just has a set of points, or a set of clusters actually. And the key method in here, or the key methods are merge1 and merge_n. Merge_n is what actually implements the clustering here. So what you give it the distance metric that you're going to use for your points, the number of clusters that you want at the end of your clustering, a history tracker, and then you also tell it if you want to print out some debugging information. So, which apparently is not used in this method. Oh, no, it is. Merge1. Anyway, so while we have more clusters than the number of clusters we desire, we're going to keep iterating. And on each step, we're going to call this function or method called merge1, and just pass it the distance metric. And all merge1 is going to do is it's going to, if there's only one cluster here, then it's just going to return none. If there are two clusters, then it's going to merge them. And if there are more than two clusters, it's going to find the closest according to the distance metric and then merge those two. So, and then the return value is going to be the two clusters that it merged. So let's look at the merge clusters code. All it does is it takes the two clusters, and for each point in both clusters, it adds it to a new list points, and it creates a new cluster from those points. And then it removes two clusters from members and adds the newly created cluster. So then the find cluster or find closest method. So what's this bit of code doing here?
What is the distance between the 2 points according to whatever method you use?
Right. So, and we'll get to the metric in a second. So it initially finds, it looks at the first two members in the cluster set, and it sets min distance to be that, and then it sets to merge to be those two members. And then it iterates through every possible pair of clusters in this cluster set and finds the minimum distance according to the metric. So, let's see. So let's look at the cluster class. All the cluster object does, or class does, is it holds a set of points. It knows the type of point that it's holding, because that becomes important when we talk about the different types of things that we want to cluster. And then it also has something called a centroid. All a centroid is just the middle of the cluster, right? If you take all of the points and you average their distances, or average their location. So these different functions, these just compute metrics about this particular cluster, right? So single linkage dist. All this is going to do is it finds the minimum distance between every pair of points in the cluster. And what does max linkage distance do? I'm sorry, I'm mistaken. It finds the minimum distance between this, a point in this cluster and a point in another cluster. I misspoke. So what does max linkage dist do? The opposite. Yeah, the opposite. I have to keep you talking, otherwise you'll fall asleep. And then average linkage dist, same thing. This is why having meaningful function names is important, because it helps you explain code. So it also has this method in here called update. And what update does is it takes a new set of points and it sets the points that this cluster has to be these new points. And then it computes a new centroid for this cluster. And the return value is the distance of the old centroid from the new centroid. And this becomes important in some of the algorithms. All right. And then there's just some bookkeeping stuff here, like members will just give you all the points in this cluster You all know what yield does, right?
We explain it.
Okay. So yield returns a generator object, which allows you to iterate over elements. So this was asked during the quiz review, what's the difference between range and X range, right? So if I have a range of values, it actually returns a different type. So like I can print out this list, right? In this case, it'll print out the type of object it is. So this is accomplished using yield. So if I wanted to write this myself, what this is going to do is it's going to return something called a generator object. And all it does is instead of holding all the numbers in memory, it's going to return them one at a time to me. So like when I use range here, it constructs a list and it has all of those integers in memory. If I use X range, it's not going to hold all the integers in memory, but I can still iterate over them one at a time.
So within that function, you're sort of calling yield a bunch of times before the function finishes, right?
Yeah.
So how is that accomplished? Is it sort of operate differently than the way that you normally think of a function sort of running and returning something?
Right. So what this tells Python is that when it sees a yield, it's sort of like a return, except it's telling Python that I want to come back to this location at some point. So it a return just returns out of the function completely. What a yield does is it takes the value that is specified after yield and it returns to the calling place in memory in the program and that value. But then when it comes time to get a new value, it'll return back to where this yield exited. So kind of a way of maybe seeing this is if I iterate over my X range, each time it needs a new value, it's going to go back inside this function and grab it. So it looks like a function, but what it's actually doing is creating what's called a generator object, and it has these special methods for getting the next value. So it's some nice syntactic sugar, but it's pretty neat. But that's what's going on with this yield statement here, is that instead of returning the entire list of points, or instead of doing it in some other way, all it's doing is just yielding each point one at a time so that you can iterate over them. All right. So what else? So here's a method for computing the centroid. All we are going to do is total up where each point is, and then take the average over all the points. Does that make sense? All right. So the example we saw was mammal teeth. And the way that that's accomplished in this set of code is we're going to define a subclass of a class point that's called mammal. And what point does is it has a name for a given data point, it has a set of attributes, and then you can also give it some normalized attributes. If you don't give it the normalized attributes, then it'll just use the original attributes. So it becomes important when we talk about, when we do scaling of our data, which we'll do in a shortly. So there's nothing really special about it, except for this distance function, right? It's just defining the Euclidean distance for a given multi-dimensional point. So everyone knows that if you have a point in 2 dimensions, then it's just, if it's an xy point, then it's just, x squared plus y squared square root of. It generalizes to higher dimensions, if you weren't already aware. So like, if I want to find the straight line distance between a point in 3D, it's just going to be x squared plus y squared plus z squared square root. That's all. And then so on and so forth. Okay. So all this does is it subclasses point, and it has this function scale features. And what scale features does is it'll take a key, and in this case we've defined 2 ways of scaling this data, scaling these points. We have the identity, which is it's just going to leave every point alone, and then we have this 1 over max, which is going to scale each attribute by the maximum value in this data set. And if we look at the data set, we know that our max value is 6, right? So you could do that automatically, but in this case, we're using prior knowledge of the data set that we have. So why don't we do a clustering? So this is going to do a hierarchical clustering, right? And what we're going to ask, if I just specify the default parameters, all it's going to do is it's going to look for 2 clusters. It's going to use the identity, and it's just going to print out the history, like when it's performed the different merges. Now, unless I have extraneous code that I'm already running. So what starts off first is we get a lot of merges with just these single element clusters, right? So we have a beaver with a groundhog, so I guess they're pretty similar in terms of teeth. We have a squirrel with a porcupine, wolf with a bear. And so eventually though, we start finding clusters. So like a wolf and a bear, I guess, are more similar, but they're also similar with a dog. So we're gonna start merging multi-point clusters. So we start seeing like the beaver and groundhog cluster is going to get merged with the squirrel and porcupine cluster. So if you were to visualize this, so like the reason why it's called hierarchical clustering is which ones did I say? Beaver, groundhog? These guys have been merged into a cluster, right? They started out as their own cluster, and and they've been merged into their own cluster. And then the gray squirrel and the porcupine, same thing. They started off in their own clusters at the beginning, they got merged. And now what this step is saying is that these two clusters get merged. So we're building this tree or hierarchy. That's where the hierarchical comes from. So we use hierarchical clustering a lot in other fields. So like in speech recognition, we can do a hierarchical clustering of the speech sounds. So if I have, say, different vowels and maybe a couple of consonants, I would expect to see, say, these kind of clustered together first. And so what I might see is these would be like fricatives, but then I might have some stops like T and B that get merged first. So like it's a way of kind of making these generalized groupings at different levels. So, does anyone have any real questions about hierarchical clustering? So should I move on to k-means? All right. So what's the general idea with k-means? So I start off with a set of data points. What's my first step?
Choose your total number of clusters.
Right, so I'm going to choose a k. So let's say for giggles, we're going to choose k equal 3. And then what's my next step?
Choose k centroids.
So we're going to pick k random points from our data set. All right, and then what do we do? Then you cluster them. Yeah, all right. So after we've chosen our 3 centroids here, these become our clusters, right? And we're going to look at each point, and we're going to figure out which cluster they're closest to. So in this case, this is going to be a pretty easy clustering. So all these points are going to belong here. All these points are going to belong here. All these points are going to belong here, right? And then we're going to update our centroid for each of these clusters. And there's going to be a distance that the centroid moves each time we update it. So in this case, the centroid moved quite a bit, right? And then we're going to find the maximum distance that the centroid moved. And if it's below a certain cutoff value, then we're going to say I've got a good enough clustering. If it's above a certain cutoff value, then what I'm going to say is like, this centroid moved quite a bit for this cluster, right? So I'm going to try another iteration. I'm going to say for each one of these points, I'm now going to try and find the closest cluster that it belongs to based on these new centroids. And in this case, nothing's really going to change. So all of the deltas, all of the centroids are going to stay the same. So it's going to be below the cutoff value, and it's going to stop. So what's an advantage of k-means over hierarchical clustering?
More efficient.
Yeah. So let's say that I have 1,000,000 points. If I were to hierarchically cluster these, that means that I'd start off with 1,000,000 clusters. And then on each iteration, I'm just going to reduce it by 1. I don't know, say 3, okay? So on each iteration, we're just reducing it by 1, which if that's all we were doing would not be so hard. It doesn't take too long to count down from 1,000,000 on a computer. But on each one of these steps, we have to compute the pairwise distance between every cluster. So it's going to be n times n minus 1 comparisons on each step, which in this first case works out to a lot. And it doesn't get much better. So approximately, right? And it doesn't get much better as we go down. With k-means, what happens is we just have to perform on each step. If we have 1,000,000 points and we have k clusters, we just have to perform k times 1,000,000 comparisons, right? Because for each point, we need to find the closest centroid, approximately. So the upshot is that k-means winds up being a lot more efficient on each iteration, which is why if you have a large number of points, you might want to choose k-means over hierarchical clustering. Okay. What's an advantage, though, of hierarchical clustering over k-means? Even though it's less efficient, what's another?
Seems more thorough.
What's that?
More thorough.
More thorough.
I mean, you can get a lot of different levels that you can look at.
Yeah, you get a lot of different levels, so you can look at the clusterings at from different perspectives. But the kind of key thing with
You don't necessarily know how many clusters there actually are. A
yeah,
hierarchical cluster will tell you like all the clusters. I mean, you can just go down to the tree and pick.
right. So you could go down different levels of the tree and pick however many number of clusters you want. But the big reason that, one of the kind of main advantages that hierarchical clustering has over k-means is that k-means is random. It's non-deterministic. Hierarchical clustering is deterministic. It's always going to give you the same result. With k-means, because your initial starting conditions are random, because you're choosing k random points, the end result will be different each time. And so when we do k-means clustering, this necessarily means that we don't necessarily want to do it once. Like if we choose k equal 3, we might want to do 5 different k-means clusterings and take the best one, right? So that's kind of one of the big points with k-means. There's a degenerate condition with k-means. So if my objective is if my stopping criteria is that the centroid doesn't move, what's a really easy way to make the centroid not move? By choosing k. Wasn't it? K equals n, right? So if I have k clusters, or if I have n points and I have k equal n, then all of my points are going to be their own cluster, and every time I update, I'm never going to move my centroid. This also, so in your problem set, you're going to be asked to compute a standard error for each of the clusters, and a total error for the entire clustering. So what that is if I have, let's see if I remember this. If I have the centroids and I have each point in, I don't know, the centroid. So what I'm going to do is I'm going to take the centroid for each cluster, and I'm going to find the distance from each point in the cluster to the centroid, and then I'm going to sum up all of those distances over the entire clustering. That's going to give me my error. I'm not sure if that equation is totally right, but that's there might be like a division in there. But the general idea is that what I'm trying to emphasize is that we can reduce this number by just increasing the number of k. And if we make k equal n, this is going to be 0. So like I was saying with statistics, you never want to trust just one number. With k-means, you never just want to trust one clustering or one measurement of error. You want to kind of look at it from multiple perspectives and vantage points. So why don't we look at the code and try and match up all of that stuff with what you'll see on your problem set. So the big function to look at for k-means is aptly named k-means. And it's going to take a set of points. It's going to take a number of clusters. It's going to take a cutoff value and a point type and a variable named max iter's. So first step, we get our initial centroids. All we're going to do is we're going to sample our points randomly and choose k of them. Our clusters we're going to represent as a list, and we are going to, for all the points in the initial centroids, we are going to add a cluster with just that point. And then we get into our into our loop here. So what this is saying is, while our biggest change in centroid is greater than the cutoff, right, and we haven't exceeded the number of iterations or maximum number of iterations, we're going to keep trying to refine our clustering, right? So that brings up a point I actually failed to mention. Why should we have this cutoff point, max iters?
It'll go forever.
Yeah, there's a chance that if our cutoff value is too small, or we have a point that's like on a border and likes to jump between clusters and move the centroid just above the cutoff point, that will never converge to our cutoff. And so we want to set up a secondary break. So we have this max iters, which defaults to 100. So with this setup, though, there's a couple of things you have to consider, and that is, one, you need to make sure that your max iters is not too small, because if it's too small, you're not going to converge. And you don't want to make it too large, because then your algorithm will just take forever to run, right? Likewise, you don't want to make your cutoff too small either. So sometimes you have to play around with the algorithm to figure out what the best parameters are. And that's oftentimes more of an art than a hard science. So anyway, continuing on. For each iteration, we're going to set up a new set of clusters, and we're going to set them initially to have no points in them. And then for all the points in our data set, we are going to look for the smallest distance. So that means we're going to initially set our smallest distance to be the distance from the point to the first centroid, and then we're just going to iterate through all the centroids or through all the clusters and then find the smallest distance. Is anyone lost by that? Make sense? Once we find that, we're just going to add that point to the new clusters. Right? And then we're going to go through our update. We're going to iterate through each of our clusters. We are going to update the points in the cluster. So remember, the update method sets the points of the cluster to be this new set of points you've given it, and it also updates the centroid, or it updates the centroid and it returns the delta between the old centroid and the new centroid. So that's where this change variable is coming from. And then we're just going to look for the biggest change, right? And if at some point in our clustering these centroids have stabilized and our clusters are relatively stationary, then our max change will be small, and we'll wind up terminating the algorithm. And all this function does is once it's converged or it's gone through the maximum number of iterations, it's just going to find the maximum distance of a point to its centroid. So it's going to look for a point that has a maximum distance from its corresponding centroid, and that's going to be the coherence of this clustering. And then it's just going to return a tuple containing the clusters and the maximum distance. So it's not a hard algorithm to understand, and it's pretty simple to implement. Are there any real questions about what's going on here? All right. So the example that he went over in lecture with k-means was this counties clustering example. So we had a bunch of data of different counties in the US, and we just played around with clustering them and seeing what we got. So if we made 5 clusters and we clustered on all the features, wanted to see kind of what the distribution would be for, say, incomes. What this function test is going to do is it's going to take a k, a cutoff, and a number of trials. So remember we said that because k-means is non-deterministic, we're going to want to run it a number of times to find, maybe we get a bad initial set of points for our centroids or for our clusters, and that gives us a bad clustering. So we're going to run it a number of times and try and prevent that from happening.
There's multiple runs. There's really different clustering patterns. How do you figure out what the sort of mean is after you run it several times?
Well, it can be tricky, to be honest. One technique you could use would be to have a like a training set and a development set. So what I mean by that is you perform a clustering on the training set, and then you take the development set and you figure out which clusters they belong to, and then you measure the error of that development set. So it's, once you've assigned these development points to the clusters, you measure the distance to the centroid, and you sum up the square distances, and you sum up overall the clusters. Then if you do that a number of times, what you would do is you choose the clustering that gave you the smallest error on your development set. And then you'd say, that's probably my best clustering for this data. So that's one way of doing it. There's multiple ways of kind of, skinning the cat. I was trying to think of a good aphorism. And actually that's what's on your problem set, or one of the problems on your problem set is to cluster based on like a holdout set and see what the error, what the effect of the error is on this holdout set. So, did that answer your question?
Yeah.
Okay. And then choosing k, there's different methods for doing it too. A lot of it is you run a lot of experiments and you see what you get. This is kind of where the research part comes in for a lot of applications. So you can also try some other automatic methods like entropy or other more complicated measurements of error, but don't worry about those. For our purposes, if you get below the cutoff value and you run a number of iterations and you've minimized your error on your test set, we'll be happy. It's just kind of, we want you to be familiar with k-means but not experts in it, because it's a useful tool for your kit. Anyway, so all this code is going to do is it's just going to keep it's going to run a number of trials. It's going to perform a k-means clustering, and it's going to look for the clustering with the smallest maximum distance. So remember, the return value of k-means is the maximum distance from a point to its centroid. We're going to define our best clustering as being the clustering that gives us the smallest max distance. So that's another way you would choose your best clustering. Yeah, and that's all we're going to do for this bit of code here is we're going to find the average income in each cluster and draw a histogram. So I think this is actually done. So we have 5 clusters, and what they're showing us is that the clusters, if we take the average income of the different clusters, they're going to be centered at these average incomes. So let's see what some other plots look like. So this set of examples is using a point type. It's called county. And county, like the mammal class, inherits from point, and it defines a set of features that can be used, or set of, it calls them filters. But basically, if you pass it one of these filter names, like all, education, no education, wealth only, no wealth, what this is doing is it's selecting this tuple of tuples. And so if I say wealth only, it's going to use this tuple as a filter. And for each element in this tuple of tuples, it has a tuple that has the name of the attribute and whether or not it should be used in the clustering. So if it has a 1, it should be used. If it has a 0, it shouldn't be used. So if we look at how that's applied, it'll get a filter spec, and then it'll just set a attribute called ATR filter, and if we see where that's used, then it's going to iterate through all of the attributes, and if a given attribute has a 1, then it's going to include it in the set of features that are used in this distance computation. So, did that make sense at all? No? So,
Is that just to make it more efficient?
well, the idea is that it's to illustrate that if you use different features when you're doing your clustering, you'll probably attain different clusterings. So in that first example I showed, we used all the features, but in this example, we are going to look at only wealth, and that includes the features. If we look at this set of filters here, it's going to include the home value, the income, the poverty, and then all the other attributes like population, change. It's not going to include. So it's not going to be; those aren't going to be used in the clusterings. So this is going to change what our clusters look like. So if we look at what we have for our clusters, well, that's not very clear. Yeah. So let's see what happens. Oh, I'm not sure if that's really going to show us. Probably better if I showed them all at once, right? So this will take a while.
So while we wait,
Yeah.
I shared this one question that's related, but there's a method for dictionaries that's like returns an iterative for a dictionary, like iter d.
It's like iter values or iter keys. Yeah.
I was wondering how to go about using that like, in actual code.
In actual code. So you know that if you have a dictionary D, you can do like d.keys.
Yeah.
So remember I was kind of demoing that code, the difference between range and X range? Same thing. If you, this is going to return an actual list of all the keys, right? What d.iter keys returns is a generator object that gives you one by one each key in the dictionary. So if you wanted to, so a lot of times you guys in your code will use something like 4k in d.keys to iterate through all the keys in the dictionary. What this method does though is it creates an actual copy of that list of keys, right? So it's when you call d.keys, if you have a lot of keys in your dictionary, it's going to go one by one through each of those keys, add it to a list, and then return it to you. What d.iter keys does is it skips that, going one by one and adding it to a new list. It just gives you a generator object, which when you use it in a for loop, it's going to just return the key or yield the key one at a time without creating a separate list. That makes sense?
It would be more efficient.
Yeah, it's generally more efficient. And then there's also, I think, inner values, which goes through each of the values. And then I think there's inner items. And I think, if I'm not mistaken, if you do something just like that, so you do 4k v in D, this is going to iterate through a tuple that contains the key and the values associated with that key. And it's equivalent to doing this. Make sense? So where are we at? Oh, maybe I shouldn't have done this all at once. So I don't know if it's going to finish. Why don't we just look at 2? Why don't we take a look at what the average incomes, or what the clustering gives us for average incomes for education versus no education. It's probably not going to be a very good comparison. It's doing 5 trials and 2 trials for each clustering. So k-means is the efficient one, which means that hierarchical will take a long, long time. There we go. So these are the average incomes if we cluster with k equal 50 on education. And then there should be another one. I didn't create the new figure. So apparently there's a bug in the code. I wanted to show the two plots side by side so you could see the differences. Because what you should see is we would see a different distribution in incomes among the clusters if we clustered based on no education versus education level. But my code is buggy and not working the way I expected it to. So I apologize.